Hey everyone, and welcome back to episode 1 of now our foray into predicate logic. And of course, this time we'll be tackling the syntax of predicate logic. And we're going to follow much the same pattern we did with propositional logic. And if you recall, the very first thing we defined in propositional logic was our friend script S, the set of sentence symbols. So let's try to first, before we get to the definition, let's try to unravel what the analog of script S is for predicate logic. So recall that script S was the set of symbols you supplied. So the point is, predicate logic, if you recall, gave you connectives like and not and parentheses. But then this magical set, script S, was a potentially variable set of sentence symbols that were basically just random characters that we supplied meaning to. So the point is, we need to uncover what symbols are constant, or a constant, I shouldn't use that because that'll be confusing, but what symbols are used throughout God, I cannot spell this word, throughout math, and what symbols vary by theory. And remember, we're building a syntax right now, so the goal is I can write down a sentence, and I can determine if that sentence is a legal sentence of predicate logic or not. That is the end goal for this episode. So, but of course, not always will I want to talk about P and Q. Sometimes I want to talk about something else. So let's uncover, it's a little more complex now, because predicate logic is going to allow us to talk a lot more about mathematical objects themselves. But as a result, we'll have a lot more symbols that are undefined in predicate logic and instead are supplied by the equivalent of script S. Okay, so let's just take an example sentence. How about the sentence, for all x, there exists a y such that x is greater than or equal to y plus 3. So let's take a moment. Which of these symbols do you think... This will eventually... I will create a syntax for predicate logic where what I have just written is a legal string, a formula of predicate logic. But what symbols here are intrinsic to predicate logic, a logic itself, and what symbols are something that we need to define elsewhere? So I claim that the only symbols that we need to define elsewhere are these three symbols here. Everything in math will have variables, and these things, you haven't seen them before, they're quantifiers. We'll get to them. But they're much like the connectives of predicate logic. And the variables, it doesn't hurt to, have variables in predicate logic, because every field of math has variables. It doesn't, right? Anyway, I don't think that's a bold statement by any means. But these three statements, for, all three of these, for instance, have no meaning in geometry. So these sorts of symbols are the ones that may differ depending on what field of math you're working in. And we want to write a predicate logic that is general enough to encompass any field of math. And as a result, these three particular symbols will be something we need to handle. So this is a constant symbol. This is a function symbol. And this is a relation symbol. And I think those notions are very self-evident what they mean. So I won't. And recall, we're dealing with syntactics right now, not semantics. So we don't really care what a function is. We just want to say what is legal and what isn't. So for instance, why is it important that we have such a separation? Well, for one, none of these three are interchangeable. So for instance, I could have y plus 3 and I could also have y minus 3, and they work in a very similar way. But I could never have x 3y as constants just need to be objects themselves. They don't operate on objects like addition does, right? These are fundamentally different things. And of course, for example, the sentence, 4 times 3 equals 6 times 2 is legal, but the sentence 4 equals 3 times 6 equals 2 is not legal, right? Functions produce numbers, but you can't have, in a relation like equality does not. So in practice, constants are objects themselves. Functions take objects and they produce objects. And, if the objects thing confuses you, let's just call it a number. But, these, in different fields of math, the objects are different things. In geometry, the objects are points and lines and planes, right? And finally, relations, of course, also take objects, right? Just like 4 equals 3 and 4 times 3 look very similar. They take objects with themselves. However, what they produce is not an object, but a proposition. 4 equals 3 is a proposition, much like P was for us before. And of course, we'll have all the logical connectives to do the same work with a proposition like 4 equals 3 as we have done in the past. So hopefully, let's end with why I wasted all of this time doing this. Hopefully, I want to motivate the next definition I'm going to give you. And my hope of the motivation is that you understand why it doesn't suffice to say, let S be a set of symbols. Because in propositional logic, there was only one type of symbol I cared for you to provide, and it was the sentence symbols. You can think of the sentence symbols as sort of the constant symbols, right? P was a constant that you could use in your logical reasoning, right? Q was a constant you could use in your logical reasoning. You think of the sentence symbols like that. However, I'm observing 3 different types of symbols that may wildly differ between fields of math, and all 3 of these different types of symbols have different syntactic rules that you can build, right? These are, you can't interchange functions and relations and constants. So we're going to need to define this in a way where these 3 things are treated separately. Okay, so hopefully with that out of the way, we can get into the actual definition of a language. And so we'll say a set of symbols script L is a language. So, and I lied a little bit. We'll just say any set of symbols is a language. But we assume that L actually looks like this. F1, or let's start with P. We're using P for relations because relations are actually, another word for a relation is a predicate. So predicate logic stems from that the core foundation of this logic is on these relations or predicates, as opposed to propositions from before. So we might have, n propositions. We might have m functions, and we might have q many constant symbols. So L will be a set that looks like this. It's just an arbitrary set of symbols, but pi are relation symbols. Fi are function symbols. And Ci are constant symbols. And so far, we have no difference between these. It's just a name and a type I haven't told you anything about them that are different, but I need to categorize them in these three ways so that when the next goal is we're going to recursively define our syntax. And so when we do that, I need to have three different types of things so I can give them different rules. Okay? So there's one other thing we need to talk about before we define syntax. So and that's arity. I think that's the right word to describe this. And this will be very quick, but a function or a relation is a function f or a relation, definition is exactly the same, is n-ary if it takes n arguments. So we are familiar with writing 2 plus 2 like this. But really, addition is a 2-ary function. And 2-ary is really binary, right? So it's a binary function. And in our syntax, so maybe I will write this down too. I'll always write 2 plus 2 like 2 plus 2, but really formally, we ought to write it as the following. Formally, we ought to be writing all functions like the functions they are, right? You've seen f of x, you've seen f of x comma y, so x plus y is really plus of x comma y. So hopefully, the reason is that if you only think about things in terms of like these strings of like 2 plus 2, you'll only be considering 2-ary functions. But there's nothing we've said anywhere that would make it, I can make a language that has function symbols that operate on 7 different mathematical objects. That's legal. We don't have to restrict ourselves to only, if we write strings like this, I can only ever have 2 things relating to each other. So really, I should be writing my functions like this, and then if I want to have, f of 1, 2, 3, 4, 5, that's legal too, right? So the point is, I could define a binary operator, but I would still have to define a function anyway to allow me to use functions. And I'm claiming that all binary operators are just functions, so all I really need to define for you is a function. Same is true of relations. Really, we'll say 2 equals 2, but we should be saying equals of 2, 2. Okay? So same thing. What if I had a relation that needed to operate on 3 different things? I would prefer the other notation. So it's the same thing where, I started using, implies and or, but really secretly in the background it was all ands and nots. So secretly in the background it's all functions and relations, but there's sufficient to express notions like addition and equality. Okay, so with that out of the way, that's the arity of a function. Let's also say, not only did I tell you what not only did I tell you the relation symbols and the function symbols, but I also told you the arity. So I told you this function takes on n attributes, and this function takes on, q many variables, right? Okay. So with that out of the way, we're going to begin our recursive definition of syntax. And this one's a little bit more complicated, but it's not actually much harder to understand. It's just a little more complicated. So we will, first things first, a little more intuition. X plus 2 is sort of an expression, right? It's not really something that's true or false. It's just, a mathematical expression. But then, something like x equals 2 is closer to like a proposition, right? This is something that does have a true or false value. So we'll use the following words. This will be called a term, and this will be called a formula. And that will be how we distinguish. Back in propositional logic, we used there was only sentences, so we just called it sentences. But now there's two different ideas. There's the nitty-gritty objects of math, and then the claims and the logical statements I make about them. So we'll first recursively define terms, and then we'll be able to use terms to build formulas. All right. And now finally, we will have a distinction between relations, functions, and constants in our definition of term. And this is actually, of course, recursive. So let's begin, and it's going to look, you've seen these recursive definitions a lot now. So, oh, I forgot one thing. In addition, remember how we had the connectives? Well, we're going to need a few other symbols. So in addition to L, we get these symbols. We get this one. This is for all. And I'll call this a quantifier. Much like how, if you remember, much like how P or Q is not P and not Q, right? Just like that. For all, there exists in X is the same thing as not for all X is this not true. So with nots and the for all, we get that there exists. So for our definitions, we won't be using there exists. We, of course, get not and. These are our connectives from before. We, of course, get parentheses. Oh, God, spelling parentheses. And finally, we get a new thing. We get a new guy, V1 through Vn, which are variables. And this is, of course, the x, the y. When I say for all x, I really mean for all vq for some q, right? So these are the fixed symbols that are not constant symbols. They represent variable mathematical objects, and we can use the quantifiers to make these variables range across sets of our choosing. Okay, so these are the symbols that we're going to need. Now, for variable symbols, for the variable symbols, I'll probably stick to using x and y mostly, but really, we should probably just index them as follows. Importantly, I'll never need every statement is finite, so I don't have to worry about ever needing uncountably many variables. Just a countably large set is fine because it will handle, every statement is finite, so I'll never need to use more than finitely many variables in a statement. So let's just say there's countably many variables and call it a day, because I know that'll be enough. Sorry, hopefully that wasn't too confusing. I know there's a lot of stuff happening. So now we need to get to the actual recursive definition. So we'll start with defining a term recursively. And let's try to think through what this ought to be. So a term should represent a mathematical object. So I claim a variable v1, or I'll actually call it a vi to be more general. A variable vi is a term. That's sort of our base case. Just like how a sentence symbol was a term, a variable is a term. That was like our base case. And now there's actually a second base case, which is, of course, a constant symbol. ci is a term. So that's sort of our base cases. So if I write down 2, that's a term. That's a mathematical object. If I write down x, that's not a fixed mathematical object, but it will always represent a mathematical object. And then how do I make more terms? Well, I use functions. If x1 through xn are terms, and if f is here comes this guy, an n-ary function, so a function that takes n inputs, f of x1 through xn is a term. Okay, so these are the terms, right? So and remember, this, we could take x, we could take 2, and then we could use a function like x plus 2 to add them together, make a new term. So the terms are what functions operate on terms to give you new terms. Okay, and then finally, 4.4 is same as always, and I won't write it down. But 0.4 is the same one as always, that terms are exactly the things I can create with this recursive definition. So I'm claiming this is exhaustive. The only things that are terms are the things that are, that this definition is an if and only if. So the only things that are terms are the things that are variables, constants, or a finite number of applications of variables and constants. If you don't remember that bullet point 4, just go back to like video 2. It's that same thing. It's gonna, yeah, right? Okay, it hasn't changed. So now we've defined terms. So let's move a little bit further and define formulas. So we need actually to make a small distinction. Remember, formulas will represent stuff like x equals 2. But there'll be a small distinction between there's a small distinction between formulas, so we'll define something called an atomic formula first. And an atomic formula is basically a formula so small that there's no formula within it, okay? And I just realized, I'm sorry for the bad order to this. Sorry. Let's write a sorry first. And then one more symbol I forgot. So equals is always allowed, and it's what you think it is. So no, even though stuff like less than or equal to, or greater than or equal to, less than or equal to, any whatever relation you want, subset, element, these are not always allowed. But in any field of math, there's a notion of equivalence, right? Because there's always going to be objects, and objects equals is a fundamental thing. The other key idea is without at least one relation, we have no way of building terms, of building formula. So we'll agree that equals is a symbol that we all know what it means. So I'm always allowed to use equals, and that way, if you gave me, for instance, if you gave me my script L to be the empty set, I can still use equals, and thus I can still build. Use that relation to build formula. Okay, so now I'm telling you equals is a separate thing from a relation symbol. So it will now occur separately in the definition. And I needed to give, I'm sorry that order was bad, but I had to give that explanation before I actually defined, before I actually gave the recursive definition, because it won't make sense why I have like two cases otherwise. So let's say if let's just write this at the start so I don't have to keep writing it. If t1 through tn are terms, then t1 equals t2 is an atomic formula. So an atomic formula is what you're going to get immediately from applying a relation. So remember, equals is something that takes terms but gives me a proposition, a truth value, right? So equals will do that, and any relation, like less than, like greater than, will do that as well, but we'll have to handle it separately because a relation is a symbol that you've provided. So similar to before, if R, yes, we'll call it R. If R is a n-ary relation symbol, then R of t1 through tn is an atomic formula. Okay, so an atomic formula is the building block. You can think of this, even though this is itself recursive, this is actually sort of the base case of the more general recursion for formula. So that is an atomic formula. And finally, a formula is defined as the following. An atomic formula is a formula. Point 2. Now get ready for this. I'm actually going to do quickly point 2. If phi, oh, I missed that. I missed our friends. If phi is a formula, not phi is. And bullet point 3, let's not waste our time with stuff we already know. Phi and psi is a formula. So far, remember, I said an atomic formula is basically a proposition, so it's not surprising that this is exactly the same definition of a sentence. There is one other thing that we have not done. So bullet point 4 is, this is the new stuff, right? So if phi is a formula, then for all x, phi is. And I should say if phi is a formula and x is a variable. And that's not surprising. So I can take any formula and I can quantify over a variable. And x doesn't even need to occur in phi. We don't even know if x occurs in phi. It doesn't matter, right? Like, it's still syntactically valid to say, for all x, 2 equals 2. Like, that's still legal, even if it is kind of stupid. So that's the formulas, right? So most of this should be very familiar. Once we use the functions and relations to build the atomic formula, then we can use exactly the same connectives that we did prior in propositional logic to build up our bigger and bigger formulas. And we also can use our new connective in a similar way. And of course, finally, same as always. And I actually left it off, but yeah. So same thing. There's always going to be this final point that says that we define the formula to be exactly the things that can be produced from a finite sequence of applications of the above rules, right? So I'm claiming everything's finite, and this is all an if and only if. That's sort of the idea. Okay, so that's where we're going to stop for today. There's more to uncover about the syntax of all of this and functions and relations, but hopefully you understand let's actually handle ourselves one final example. So, for all x, there exists a k such that x equals k plus 4. Okay, maybe a claim like that. So we have our constant symbol 4, which is a term. So that's a term. We have a variable k, which is a term. And then we have this guy, a function symbol. So we really take a function of k and 4, and that produces this idea of k plus 4. And then on the other side, so this whole thing is a term, because I took a variable, which is a term, a constant, which is a term, and I used a function to produce a new term. Of course, x over here is a term. Now, getting larger, we take here equals of t comma t, right? So these are two terms. So we use a relation. We use, in this case, equality, but it could have been a relation we defined, like greater than, to produce a atomic formula. And of course, these yellow things over here are the terms. And then finally, in green, let's do the atomic formula phi. We simply say exists k of phi is formula. And for all x exists k of phi is a formula. So finally, to get the whole picture here, we use, we have the, I need even another color, right? So we have the constant symbol and the variables, and we use functions to bring them together. Well, they themselves are terms, but we can also use functions to bring constant symbols and variables together to form new terms. And when we're done with all that, we take terms and unite them together under a relation to form an atomic formula. And finally, we take an atomic formula and use logical connectives. In this case, our quantifiers, there exists and for all. We use our quantifiers to unite together, or in fact, we could unite together multiple atomic formula using the conjunction connective. But we take our atomic formulas and we use our logical connectives to build up our formulas. And that's all of the formulas. So that's how we know what a legal sentence in predicate logic is. So I know that was a confusing definition, but hopefully this is enough intuition that you understand why we have these three different classes of things: constant symbols, relation symbols, and function symbols, and also why there's a distinction between terms and formula. Okay. So we'll stop there. Next time we will dive a little deeper into, we'll do a little bit more syntax and talk a little bit more about all these symbols, and we'll also start to build the definition of a model. So thank you guys for watching, and I'll see you in part 2.